Considering what we discussed in the last class, let's sum up. First, we have seen that suppose number one, that suppose it is given that T is a linear operator mapping V to V, and dimension of V is given to be some finite integer n less than infinity. Then, if you have got some eigenvectors T V I as lambda I V I, where V I not equal to 0 and V I belongs to V, that is V I at some V I is a non-zero vector belonging to V such that T working on V I gives you back V I only, just multiplied by a constant lambda I. Then we say V I is an eigenvector and lambda is the corresponding eigenvalue for this operator T. Now, suppose we know we have lambda 1 not equal to lambda 2 not equal to dot 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 equal, not equal to say lambda r, that is a set of r distinct eigenvalues, or distinct eigenvalues eigenvalues in short I will write eigenvalue in short I will write as EVL eigenvalue, and eigenvector just EVR. Okay, this is my no, because eigenvalue, eigenvector, you have to write so many, two words. So, EVL, EVR. So, distinct EVLs and R less than equal to n. Why less than equal to n? We will see very soon. Then we have seen, that the corresponding eigenvectors V I equal to 1 dot 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 R linearly independent, that we have seen that eigenvectors corresponding to this different eigenvalues, distinct eigenvalues, they are linearly independent, that we have seen last time. Okay. So, no. Secondly, we also have seen that we have also seen the concept of eigen subspace corresponding to a particular eigenvalue, say lambda I. That is, suppose I consider this say W lambda I as what? It consists of those vectors belonging to V such that T working on V gives you nothing but the chosen lambda I times V. Okay. Then this is eigen subspace. Corresponding to lambda I. Remember one thing, when I say eigenvector, it is strictly non-zero, but when I write W lambda I do not mention the condition that V is not equal to 0, because if it is a subspace, it has to have the 0 vector. So, I am silent. Okay. Why it is a subspace? We have seen last time that suppose V1 and V2 belongs to V, belongs to this W lambda I, then any combination C1 V1 plus C2 V2 also will belong to W lambda I, simply because if we apply T over this vector using linearity, we will have C1 T times C1 times T V1, which is lambda 1 V1, and C2 times T V2, which is lambda 2 V2, then again a linear combination of V1 V2, which means this content is closed. Okay. That is if I take say T over this we did last time, then using linearity T should be working on V1 and T should be on V2. T V1 is lambda 1 V1, lambda I V1, T V2 is lambda I V2. So, you can take lambda I common and you get back the same vector. That means, if V1 and V2 are two eigenvectors, then C1 V1 and C2 V2 also, that is if V1 and V2 belongs to W lambda I, then C1 V1 plus C2 V2 also belongs to W lambda I, because T working on that gives you the same vector itself, just multiplied by the same eigenvalue lambda I. So, therefore, if V1 and V2 are member of W lambda I, so any linear combination of them also is a member of W lambda I, which shows that this is eigen subspace. For this eigen subspace, if I consider the dimension, so I denote it by Ni. Okay. This also you have seen. I am just writing down the main points of what we did last time. Number 3, suppose we have got distinct eigenvalues lambda 1 up to lambda r. We have eigen subspace W lambda 1, eigen subspace W lambda 2 dot 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 eigen subspace W lambda r, and suppose I form W as the direct sum. It has to be direct sum because, as you know, as I have shown, that any vector belonging to W lambda 1, any vector belonging to W lambda 2, they are forming a linearly independent set, isn't it? Therefore, when I am summing, when I am considering the combination, it has to be a direct sum. This means, if you consider one basis of W lambda 1, one basis of W lambda 2 dot dot dot, one basis of W lambda r, you append all those basis vectors, then you get a basis of W. The resulting, I mean, it's a basis because the resulting set also is linearly independent and it spans W. Fine, this we know. If it, and clearly W has to be, I mean, within V. If W is equal to V, then we have V is equal to W lambda 1 dot 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 W lambda r. Then we say T is diagonalizable. Number 1, why diagonalizable? I will come to that, but we just say T is a diagonalizable operator on V, and clearly dimension n, there is a dimension of vector space V will be equal to dimension of W lambda 1 plus dimension of W lambda 2 plus dot 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 plus dimension of W lambda r, which is Ni, summation of this I equal to 1 to r. Okay. These 2 points follow. This is 1 point, this 1 point, these 2 points follow. We just give it name T diagonalizable operator. Why we say so? To understand that, we come back to the basic property of operators as a diversion from here. Suppose we are considering, that is, we are presenting some other result which is relevant here, and that I am showing here. Suppose I am considering any linear operator V2, say any V prime. Then my claim is T can be defined simply by taking any basis of V. If dimension of V say equal to n, and you say any basis, say u1 dot dot dot, say un, a basis of V. Then my claim is T can be defined perfectly if we are given the action of T on each of the basis vectors. That is, if I know what is T u1, if that is given to me, if I know what is T u2, that is, if that is given to me, dot dot dot, if I know what is T un, mind you, T u1, T u2, dot dot dot, T un, they all belong to V prime, because that is where the vectors from V are mapped to. Okay, if these are known, that is, if T ui known I equal to 1 to n, then for any V, element of V, we can write V as some linear combination of these basis vectors I equal to 1 to n. So, how to compute TV? If I know T ui, it is very simple. T will be working on this, and using linearity, it will be nothing but Ci T working on ui. So, if this T ui is unknown, okay, for any vector I can find out what its map will be, TV will be known. That means any operator actually can be defined perfectly just by, just by defining its action on the elements, on the basis vectors of any basis of V that we choose. Okay. If I know them, then action of T on any arbitrary vector, say V here, can be easily worked out, okay, using these known values. So, this is an elementary result of linear operators. Now, using that and using all these results, I will try to explain what do I mean by diagonalizable operator. But remember, it is a diagonalizable operator if, we have this, that the entire vector space V is given in terms of a direct sum of the individual eigen subspaces corresponding to the distinct eigenvalues of T. Okay, then I will call T as a diagonalizable operator. Actually, it is quite simple, that suppose I consider a basis of W lambda 1, a basis of W lambda 2, dot dot dot, a basis of W lambda r, okay, and append them, then that will be a basis of the original vector space V. On that basis, if I apply T on each of the basis vectors, the result will be can be written down very easily, and that is what takes us to diagonalizability. Okay, that is suppose some elements I am considering the ith eigen subspace, okay, that is W lambda I, that eigen subspace corresponding to lambda I. If I pick up vectors from here alpha I and k will be say from 1 to n I is the dimension of W lambda I, and if this is then a basis of W lambda I, okay. W lambda has dimension ni, there are ni components here, right, alpha I 1, alpha I 2, alpha I 3 dot 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 alpha I in the subscript ni. So, ni components, they are linearly independent, they form a basis of W lambda I, so I am calling it a basis of W lambda I. And these are for I equal to 1, that is eigenvalue 1, I equal to 2, eigenvalue 2 dot 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 I equal to r, eigenvalue r, okay, eigenvalue lambda r, okay, for lambda 1, lambda 2 up to lambda r. Then obviously giving from the from that direct sum decomposition result, that is from this result we can write down that if I append this, that is if I append these basis vectors, there is first start with lambda 1 dot 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 alpha 1 up to n 1. So, this is the basis of W lambda 1, then alpha 2 1 dot 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 alpha 2 n 2 dot 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 dot, then alpha 1 alpha r 1 dot 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 alpha r in r. Okay. Then this is, you can call it a set B, this is a basis of V, right, this is a basis of V. Therefore, if I have to define the operator T, I can simply take its action on each of the basis vectors and give you the result. Then the entire operator T is defined, and giving any arbitrary vector V, I can write down the action of T on that simply in terms of this result. That is, if I know T working on alpha 1 1, T working on alpha 1 n 1 dot dot dot, then I know, I can write down the action of T, that is given any arbitrary vector small v element of V, what is T V, that I can easily write down, that follows from just a discussion we had a few minutes back. But what is the action of T on them? Pick up any one, T of alpha, say particular one, say I k, this will be nothing but the same vector multiplied by the eigenvalue lambda I. So, this definition is very simple, that is T working on a particular vector here, basis vector, gives you the same basis vector. It is like, if there are like position vectors in a space, T working on a position vector does not change the direction of the vector remains same, only its length, there is a magnitude changes, there is an factor of attenuation or amplification, you can say gain factor of lambda I. That is the beauty of eigenvector. So, that means T, action of T on each of the basis vectors here is very simple. I do not need any other expression, just the same basis vector itself, just multiplied by the corresponding eigenvalue. This results in diagonal, then it is called the operator, then we say that the operator is diagonalizable actually. Now, how diagonalizable, what is diagonal here? To understand that, we have to now take the special case of operator as the matrix. That is, so long we are discussing in a very abstract way, abstract vector space and abstract operators and all that. If we consider the special case of matrices, then we will see that a matrix under such case, matrix operator under such case will become, it can be converted into a diagonal matrix, equivalently a diagonal matrix. So, you can see this, that is, suppose we consider A, or even why A, say T, because T is a matrix. Okay. It takes you say R n to R n, that means T is n cross n. It takes n into one vector, column vector, maps it to R n. So, it is a square matrix, so I am considering suppose this T. And in the same way, T has got distinct eigenvectors, distinct eigenvalues lambda 1 to lambda r is less than or equal to n, and T is diagonalizable. It is given that T diagonalizable that is Rn can be written as a, that is Rn, that the vector space can be written as W lambda 1, which is the vector space, the eigen subspace corresponding to the eigenvalue lambda 1. It will consist of column vectors of length n cross 1 each. Okay, each is an eigenvector of T corresponding to the eigenvalue lambda 1. Everything same as before, only thing is we have given a specific structure to the operator and to the vectors and all that. So, vectors are all of column vector type of length n, and the operator is a matrix or a square matrix of size n cross n. Okay. And given that T is diagonalizable, which means the vector space Rn can be written as a direct sum of the various eigen subspaces corresponding to distinct eigenvalues. This is given to you. And I will again use the same basis notation for W lambda 1, W lambda 2, W lambda dot dot dot. Then suppose I multiply T with a matrix formed like this. I just place these basis vectors. Now, each vector is a column vector only. There is only difference. Each vector is an eigenvector, but they have a specific structure. That is, they are not arbitrary. Not abstract symbols, but they have a specific structure. That is, each of them is a column vector of size n. In fact, real value vectors you can say, because I have taken R, though it could have been complex also. So, just the difference is that they have a specific structure. That is a column vectors. Otherwise, property wise, everything is same. So, suppose I put the column vector side by side as in this order only. Okay. Say alpha 1 1, the column vector, then alpha 1 n1 column vector, then alpha 2 1 column vector dot dot dot, alpha 2 n2 column vector dot dot dot, alpha r 1 column vector, alpha r nr, the column vector, and you can call this a matrix B. Then T working on this column vector is nothing but, since it is eigenvector, it will be nothing but this eigenvector itself multiplied by lambda 1. T working on alpha 1 n1 will be nothing but alpha 1 n1 multiplied by the same eigenvalue lambda 1. T working on alpha 2 1 means it will be alpha 2 1 multiplied by the eigenvalue lambda 2, so on and so forth. Okay. So, resulting thing also will be a matrix of those column vectors. Okay. And you can easily check that if you call this B, you can easily check that this will be B times a diagonal matrix D, where initially it will be lambda 1 dot dot lambda 1, how many times? n1 times. Then lambda 2 dot dot lambda 2, how many times? n2 times dot 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 lambda r dot dot lambda r, how many times? nr times, and 0 0 diagonal matrix. That is why n1 is called the multiplicity of lambda 1, n2 is called the multiplicity of lambda 2 dot dot dot, nr is called the multiplicity of lambda r. Okay. Before that, I will come to that again. Consider this matrix B. It is a square matrix. It is because total number of column vector is same as the dimension of the vector space. That is very important. So, if the vector space V had dimension n, then I have told, since we can have like this direct sum decomposition, if you add the dimensions of the respective eigen subspaces, that should be equal to n. So, that means if you count the number of columns, that is equal to n. That is very important. That is why it is n cross n matrix, and the columns are linearly independent, they form a basis of B. That means we have got a square matrix which is having full column rank, and therefore it can be it is invertible, going by our last day's discussion. If it is invertible, then we can write B inverse, if we multiply by B inverse on both sides, B inverse T B is this matrix D. Okay. Or alternatively, T is equal to B D B inverse, either form. So, this is called the diagonalization. T and D are called similar matrices. Okay. And given T, we diagonalize T by this method, we get a diagonal matrix. In the diagonal matrix, the diagonal matrix D consists of only a diagonal non-zero diagonal entries, not non-zero, some eigenvalues could be 0 also, but it is mainly consists of it is diagonal, okay, and other it is diagonal matrix, and diagonal entries correspond to the eigenvalues of T. Each eigenvalue, lambda 1 occurs n1 times, where n1 is the dimension of W lambda 1, lambda 2 occurs n2 times, where n2 is the dimension of W lambda 2 dot 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 dot, and the n1 is also called the multiplicity of lambda 1, that is the number of times lambda 1 occurs in this diagonal matrix. So, in general lambda I has a multiplicity ni, means it occurs ni times in this diagonal matrix. And what is ni? Ni is the dimension of W lambda I. That means dimension of the eigen subspace W lambda I indicates the multiplicity of the eigenvalue lambda, remember. That means Ni, which is dimension of W lambda I, also is multiplicity of lambda I. Okay. All these basic results are very important in signal processing, So, though our purpose is to take you finally to SVD and all that, it is important that we do all these. Okay. Next, now consider, now we will generalize further. Okay. I mean, we will consider the case where T is an operator from V to V, of course, and therefore T has distinct eigenvalues. But instead of taking from lambda 1 to lambda r, say for a change, say let us take from lambda 0 to lambda r, lambda 0, lambda 1 to lambda r, and they are distinct. So, lambda 0 not equal to lambda 1 dot 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 not equal to lambda r. Out of this, one of the eigenvalues I will take to be 0 value. Okay. That is, it takes, others are non-zero. That means I will consider T from V to V lambda I equal to 0, 1 dot dot dot. So, I start with 0, distinct EVLs eigenvalues, okay, W lambda I eigen subspace corresponding to lambda I, dimension of W lambda I is Ni, and we have the additional condition that lambda 0 is 0. Also W lambda 0 is 0, we then denote as W 0. Given T, given diagonalizable, meaning V is W 0, then W lambda 1, lambda r. Okay, this is what is given. Then our claim is this T operator which takes V to V, its null space will be given by W 0, that is this much, and its range space will be given by this. Okay. That is first result, null n of T, there is null space, in case you have forgotten the notation, null space of T is identical to W 0. How? To show it, suppose you take V element of W 0, that means T V is equal to eigenvalue 0 times V, which is 0 vector. This means V is element of N T also, means W 0 is contained in N T. On the other hand, it is given this, again given V element of N T, we have T V is vector 0, vector 0 is 0 times vector V, because we know the scalar 0 times any vector will give you the 0 vector. That was the very first thing in vector space axioms we have, I mean vector space theory that was done in the class. That means because T V 0 means T V equal to 0 scalar times V, that is an eigenvalue 0. That means V is an eigenvector. Okay, V is an eigenvector. For, of course, I am taking V to be non-zero here. And if this is only 0, then NT and W0 they it's very simple, it's trivial, they consider only 0 vector. Forget about that case. So V is an eigenvector corresponding to eigenvalue 0. Okay, V is an eigenvector corresponding to eigenvalue 0. That is what I am writing. That means V belongs to W0. V is part of NT, V is part of W0 also. So it is NT contained in W0. This implies this. Okay. So this is W0 is the null space of that operator T. And now we have to show that range space is given by this. This is given by, this is RT. This is NT and this is RT. This you have to prove that RT. RT is a range space. That is another point to show that R of T, which is same as range space of T, this is equal to W lambda 1, that is eigenvalues which are non-zero. I am considering only them and their respective subspaces and forming the direct sub. This is the range space that we have to prove. How to prove it? Now, we know B as the basis of V. We had already seen it. In case you have forgotten, what was B? We took the basis of each of the eigen subspaces, alpha 1 1 to alpha 1 n 1, then alpha 2 1 to alpha 2 n 2 dot 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 alpha 1 to alpha n r. That was B. That means, given any vector small v of capital V, we can write it as a linear combination of these fellows. Okay. That means, any V can be written as a linear combination them that we can write as a double summation. The vector is for the ith eigen subspace alpha I and k will go from 1 to the respective dimension. There is a number of elements in that basis, and I will go from eigenvalue 1, eigenvalue 2 to eigenvalue r. That means, I will go from 1 to r, and it is a linear combination. So, this there will be combiner coefficients, there will be 2 indices I comma k. Okay. So, this is the typical description of a vector V in terms of that basis B chosen. In that case, TV, where will TV be? TV means T will work on this linear combination, and using linearity of T, T will work directly on this vector. For I equal to, in fact, I am sorry, it should be I equal to 0, because we consider the case where now, I mean, we have got the eigenvalues from W0, from lambda 0, which is 0 eigenvalue, to lambda r. Okay. Lambda 0 is actually having the value 0. So, you have got actually r plus 1 distinct eigenvalues, as I did in the previous slide, that is lambda 0, which is actually 0, then lambda 1, lambda 2 dot 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 lambda r. That is why I am starting I equal to 0 going up to r. Okay. Now, when T works on this, first consider I equal to 0 case. For I equal to 0 case, I have got the vectors alpha 0 1, alpha 0 2 dot 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 alpha 0 n 0. They are all belonging to the null space, or T working on them will give you, or they all have 0 eigenvalue associated. That means, when T works on them, they will get multiplied by scalar 0 and they will become 0. So, that means, I mean, they do not contribute anything. Otherwise, that means I can start at I equal to 1, not at 0, go up to r, k equal to 1 to n I c I k, T directly working on, as I told you, I equal to 0 case is ruled out, because for I equal to 0, these eigenvectors actually have eigenvalue 0, or equivalently they belong to the null space. So, T working on them will give you nothing but 0 vector. So, they are, I mean, eliminated from the sum, and here I have got the same thing, same summation C I k, but they are eigenvectors. So, lambda I, you can even put lambda I here, lambda I same alpha k I. Okay. So, it is a linear combination of those eigenvectors, of those basis vectors for this space. If you call this to be equal to W, okay, what is the basis of W? If we append the basis of W lambda 1 to that of W lambda 2 dot 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 to that of W lambda r, okay, then you get a basis of W, and this linear combination is nothing but what? It is a linear combination involving those basis vectors. Okay, because for I equal to, we started I equal to 1, k varies from 1 to n1, so that covers the basis vectors of w lambda 1, just a linear combination, same for other lambdas also. Okay, so that means this is contained in w. So that means because T v belongs to or T, that is if you consider the range space of T, any vector there can be written as some kind of T v. Okay, T v belongs to, I know, R T, and T v belongs to, that is this actually for any vector. I have not written, for any vector belonging to the range space, we can write it as some T v for any some v belonging to v, because range space only consists of action of T on the elements of v. So, any vector if you pick from the range space R T of T, basically it can be written as some kind of T v, where v is some vector of v, but that vector I write as a linear combination of this basis vector starting at I equal to 0 up to R and all that. T works on that, and that gives you this. That means range space is contained in W. On the other hand, again, if V belongs to W, V will be a linear combination of those basis vectors. V should be R equal to 1 to n I, k equal to 1 to, sorry, I equal to 1 to R, k equal to 1 to n I, maybe some other coefficients d I comma k, alpha I k. Okay, that is the basis vectors of the subspaces and a linear combination. Okay, because W is nothing but the direct sum, W is nothing but the direct sum of this distinct eigen subspaces. Okay, so therefore, any vector belonging to W, you can write like that. In fact, why V? You can call it even W. That is better, vector W. Okay, there is any vector can be belonging to capital W can be written like this. But you see, this I can also write as this I have written. I can simply divide it by lambda I, because lambda I not equal to 0. 0 eigenvalue case has been separated out. Here I starts from 1. Okay, so I can divide by lambda I and multiply it by lambda I, and therefore I can write it as I equal to 1 to R, k equal to 1 to n I, d I k by lambda I, T working on, because T working on this will give you the same vector alpha I k, but multiplied by the corresponding eigenvalue lambda I, and then using linearity, this is nothing but T can be taken outside the summation this scalars times this vector. But what is this vector? That means is T working on some vector. So that means this belongs to, this thing belongs to R T. So this means W also belongs to R T, a subset of R T, which means R T is same as this W. So this is the range space of T. This also shows, if this is the range space, what is the dimension here? Dimension is n1 plus n2. That is, if you sum up the dimension of the respective subspaces, here you have got n1, here you have got n2 dot 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 nr. What is the dimension of W? n1 plus n2 plus dot 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 plus nr. So that is the dimension of W, means dimension of the range space, means rank. So that means, what is the rank of T? n1 plus n2 plus dot dot plus nr. There is multiplicity of non-zero eigenvalue, say 1, plus multiplicity of another non-zero eigenvalue 2, plus dot 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 multiplicity of another non-zero eigenvalue. So that means summation of multiplicities, summation of multiplicity of non-zero distinct EVLs. EVL means eigenvalues. This is the rank. So, find out what are the distinct eigenvalues and which amongst them are non-zero. Just pick up the non-zero distinct eigenvalues and find out their multiplicities, add the multiplicities, that will be the rank of T. Okay. Then we now come closer to that SVD. We now take this case of matrices. That is, we now take a matrix A of size n cross m, that is belonging to its of this form n cross m, means it is taking vectors of length m and multiplying it and giving a vector of length n. That means it is mapping R m to R n. On the right side, I take the case A transpose, which is R m cross n. By the same token, it is taking R n and mapping to R m. Then you consider this A transpose A. Obviously, A transpose A is a square matrix, size m cross m only. He takes R m, but gives you back R m only. It is a square matrix, like the operators we considered earlier, V to V, R m to R m. Similarly, on this side, A transpose n cross n, this maps R n to R n itself. Okay. These are all square matrix and symmetric matrix. Square symmetric, square symmetric. Real symmetric matrix, Hermitian matrix actually, square. In fact, they are all, we know they are actually non-negative definite. Okay, that we can easily see, and we have done it many times in this course. Any matrix of this form is a symmetric matrix and non-negative definite, because if you take a non-zero vector x multiplied by x transpose and pre-multiplied by x transpose multiplied by x transpose A transpose A x, you can write it as norm square of A x, which is always real and non-negative. And for such matrices, we have shown that the eigenvalues are real and non-negative, and also we have seen one more thing, that if you consider two distinct eigenvalues, the corresponding eigenvectors are orthogonal or maybe orthonormal. We have seen it in the case of correlation matrices, and that time we proved it. Okay, eigenvectors corresponding to distinct eigenvalues, they are actually orthogonal and they can be normalized, that is each having norm 1, and therefore you can say they are orthonormal. Now, this is given to you. We had also seen, we have seen that null space of A, that is on subspace of R m, on which if A works, I give you 0 of R n, that is same as null space of A transpose A. Okay, we have proved it in the previous class, and therefore, we have seen rank of A and nullity of A together is m, that is rank of is m minus nullity of A, and rank of A transpose A is again is what? Rank of A transpose A plus nullity of A transpose A is equal to m. So, rank of A transpose is m minus nullity of A transpose A, but null space of A transpose A or A are same. So, they have the same dimension, the same nullity. So, therefore, the two ranks are same. That is, in case you have forgotten, m minus nullity, there is a dimension of the null space of A, but null space of A and null space of A transpose A, they are same. So, m minus as well as nullity of A transpose A, because the two spaces are same, so their dimensions are same, but this is equal to rank of A transpose A. This you have seen in the previous class. In a similar manner, you can even call A transpose as A prime, and all this theory can be worked on this side. Null space of A transpose will be same as null space of A transpose, and rank of A transpose is same as rank of A transpose. Okay. In matrix theory, in very elementary matrix, we have seen that rank of A and rank of A transpose are same, which means rank of A transpose A and rank of A transpose are also same. We can see that in another from another angle here also. So, you do not have to even remember that elementary matrix theory that rank of A is same as rank of A transpose. The fact that rank of A transpose A and rank of A transpose are same, that will come even from another angle of this thing, another logical argument which will come. So, for the timing we keep here. Okay. Now, suppose now I prove some basic results, that is, if x EV this eigenvector of say A transpose A for eigenvalue lambda, meaning A transpose A x lambda x and x is not equal to 0, then A transpose, if you consider this vector A x, then A transpose A x is lambda x, if you put that back, is again lambda A x. So, that means in that case A x is what? Is an eigenvector EVR of this matrix A transpose with EVL lambda. Similarly, if x is an EVR of A transpose, meaning A transpose, not A transpose, A transpose, meaning A transpose x is with EVL equal to lambda, meaning A transpose x is lambda x and x not equal to 0, then A transpose x, if you carry out, what will you get? You can take A transpose and A transpose x is lambda x, so you will get lambda A transpose x, meaning A transpose x is an EVR of this matrix A transpose A with EVL equal to lambda. This means if lambda is an eigenvalue, here it implied if lambda is EVL of A transpose A, then lambda also EVL of A transpose, and this implies if lambda is EVL of A transpose, then lambda also eigenvalue of A transpose A. This only means that A transpose A and A transpose have the same eigenvalue. If lambda is an eigenvalue of A transpose A, it is the eigenvalue of A transpose, and if it is an eigenvalue of A transpose, it is the eigenvalue of A transpose A. So, that means A transpose A and A transpose have the same distinct EVLs, not eigenvectors, only EVLs. Eigenvectors are different, one of length n, another of length m, or totally different, but their distinct eigenvalues could be like this. One is a 0, one could be 0, so I am keeping a provision of 0 eigenvalue, and then one could be a lambda 1, lambda 2, dot 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 lambda r. Okay. We have also seen, I have repeating the argument, that A transpose A and A transpose, they are symmetric matrices, in fact non-negative definite matrices, and therefore eigen subspaces corresponding to W lambda 1, W lambda 2, lambda 1, lambda 2, they are mutually orthogonal, because we have already seen that eigenvectors of Hermitian matrices belonging to distinct eigenvalues are mutually orthogonal, and within W lambda 1 we can construct a basis which is also orthogonal by Gram-Schmidt procedure. So, thereby I can construct an orthogonal basis of the entire vector space R m. Okay. I mean, actually we had made a statement earlier, we will not prove that A transpose A and A transpose, they are diagonalizable. That is, I mean, if you consider the distinct eigenvalues corresponding eigen subspaces, if you find the orthogonal basis of all the distinct eigen subspaces, append them, you get a basis of the original subspace. Okay. If you are considering them as the eigenvalues for A transpose A, then by this process, I mean, you will get W lambda 1, W lambda 2 all belonging to R m, and you find out their orthogonal basis, append them, you get an orthogonal basis of R m. Similar logic for R n. Okay. But there is a separate point. Okay. Now we show, in fact, these values are called singular, this is very important, singular values of A, and they are real and greater than equal to 0. That means lambda 1 dot 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 lambda r are strictly greater than 0, because they can be either 0 or greater than 0. So, 0 have separated out. So, lambda 1 to lambda they are strictly positive, and there is one 0. They are called the singular values of A, and this will take us to the singular value decomposition. Okay. We only have to show that if suppose W lambda 1, W lambda I, it belongs to R m and is the eigen subspace of what? The operator A transpose A, which works on R m, gives you R m, takes you to R m. So, that operator, that is an eigenvalue lambda I, the corresponding eigen subspace, that is eigen subspace with respect to eigenvalue lambda I. Okay. And similarly, for the same eigenvalue, W I prime, this is actually same eigenvalue lambda I, and because they have the same eigenvalue. So, if lambda is here, lambda is there, lambda corresponds to a eigen subspace W lambda in R m and W I lambda I prime in R n. If dimension of W lambda I is say n I, dimension of W lambda I prime is say n I prime, there is multiplicity of lambda I in A transpose A is n I, multiplicity of lambda in A transpose matrix is n I prime, then we prove that n I and n I prime are same. So, the two multiplications are same, we prove. It is not difficult. Suppose we consider u 1 dot 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 u n I as a basis of W lambda I, okay, as a basis of W lambda I. That means each is an eigenvector. Okay. Each is an eigenvector corresponding to lambda I. This means we have already seen if u1 is an eigenvector of A transpose A, then A u1 also is an eigenvector of A transpose for the same eigenvalue. That means A u1 dot 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 A u n I, they belong to W lambda I prime from our theory, because we had shown earlier that A transpose A has an eigenvalue lambda and eigenvector x. Then A transpose will have the same eigenvalue lambda, but eigenvector A x. So, if u1 here, A u1 here, if u n I here, A u n I. So, they are all eigenvectors of A transpose for the same eigenvalue lambda I. So, they all belong to W lambda I prime. I will show that they are linearly independent. That is, this set linearly independent, you can see. That is, if you form C I A u I equal to say 1 to n I and equal to 0, C I should be 0. That follows very easily. This you can write as A on that means Cy Uy I equal to 1 to Ni should belong to what? The null space of A. What is the null space of A? Null space of A, and null space of A means W0, that is the eigen subspace corresponding to the eigenvalue 0. Okay, but where from Ui's are taken? Ui's are taken from W lambda I. Okay, W lambda I. So W lambda I and W0, but this also belongs to W lambda I, and W lambda I intersection with W0 is nothing but only the 0 vector, because this is corresponding to eigenvalue 0, this is corresponding to eigenvalue lambda I, they are distinct, and therefore the corresponding eigenvectors, any vector from here, any vector from here, they are linearly independent. So only place where these two subspaces intersect is 0. That means summation Ci Ui is 0, but U1 to Uni, they are basis, so they are linearly independent. So that means Ci equal to 0, I equal to 1 dot 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 Ni. This only means that these elements are linearly independent. That means dimension of these elements are linearly independent, right? That is AU1 dot 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 AUNI linearly independent. That means dimension of W lambda I prime, which is actually Ni prime, it is greater than or equal to Ni. Total number of elements here is Ni. They are linearly independent, contained in this. So dimension of this cannot be less than Ni. So it can be greater than or equal to Ni. But we will show that actually it is actually equal to. If not, now suppose we take any vector. Okay. It is like this, that suppose Ni prime greater than Ni. Then you take a vector, take V from W lambda I prime, but outside the span of AU1 to AU Ni. There is these vectors which are linearly linearly set within W lambda I prime. They span a space. Go outside that, still you remain in this, and take a V from there. That V is an eigenvector of A transpose corresponding to eigenvalue lambda I. That means A transpose V is an eigenvector belonging to W lambda I with the same eigenvalue, because I said that if A transpose has an eigenvalue lambda I and eigenvector V, then A transpose V is an eigenvector for A transpose A for the same eigenvalue lambda I. So A transpose V is here, and if A transpose V is here, then if this is an eigenvector, then A working on that means A working on A transpose V will take you inside this. Okay, this is an eigenvector, but A transpose V will be what? A transpose V. Okay, actually this needs little extra. So in the next class, because the time is short, so I will pick it up in the next class. I will just work out this proof there. Okay, we will start from here in the next class. Okay, thank you very much.